the meaning of what?
Letter B. You have some. If I remember, it was something with units. The Excel file.
Okay, so let's go back here.
This
Okay,
one, yeah. B, the letter B. What's the meaning?
That's beta.
Ah, beta. Okay. And I saw. Okay.
Okay, you remember beta? This one.
Ah, okay, it's beta. Okay. We can calculate it. Oh, it will give us.
Yeah, yeah, beta is calculated. So beta is the fourth root of k. So beta,
okay,
the fourth root. Yeah, so go back here. Beta is the fourth root of k over 4ei, right?
Okay, thank you.
Oh. Oh. I hate writing on Zoom. E is here, I is here. And again, please remember to keep your units straight, because megapascals is basically defined as newtons per millimeter squared, and this is centimeters. So you need to convert your I from centimeters to millimeters. Any other questions? Okay, so we did both of these. We should be fairly clear what we did. Please, between now and next week, work on the class problem that you have. There's a beam and elastic foundation problem, and if it doesn't work, if you're not clear, either email me or call or wait, and we can go over it again in next week's class again if not clear. Okay. So we mentioned the fact that the beam and elastic foundation results are sensitive to the loading, both the static and dynamic. It's sensitive to the track modulus. It's section sensitive to the rail section, the moment of inertia. E is an input, but E is not a variable. E is pretty much a constant. So these are the three variables that go into the equation. So if you look at the sensitivity, so this is deflection as a function of dynamic load, which means a function of speed. And no big surprise, the faster you go, the greater your dynamic load. The greater your dynamic load, the greater your deflection under the wheel, and the greater the deflection in the uplift zone. Very straightforward. Higher dynamic load, higher deflection on both sides, down deflection and up deflection. By the way, notice, this is fairly important, notice that although the dynamic load curves are different, they all cross the x-axis, or they all cross this axis, the x-axis, at the same point, which means the crossover point is not a function of speed, it's not a function of load, it's a function of k and I. Now, and then you can see that here. So this is my deflection as a function of track stiffness. So let's go back a little bit, just remember a little bit what we said about track stiffness. Very soft track is 3 to 7, 3 to 10 megapascals. Medium track is sort of 15 to 30. And then really stiff track, good track is between 30 and 50 plus, going up to 70 in the case of slabs. So if I look at my sensitivity analysis, this is really soft track over here. This is even not the stiffest track around. This is just a good medium track. okay? But you can see the greatest deflection occurs on the softer track. The least deflection occurs on the stiffer track, which is an engineering behavior that you expect. But also notice how the location where they shift, where they cross over from the down deflection to the uplift deflection shifts. So you can see that varies also as a function of stiffness. With the softer track deflecting further out. So you can see the softer track is shifting somewhere around 3.2 meters. The stiffer track is shifting at roughly around 2.5 meters. So in addition to deflecting, so what's happening is it's spread out more. Just remember, you can think of this as your rail. So this is my wheel over here. Such a bad drawer with this thing. You can see the soft track is spread out more. If I match the mating side, it would look like that. And so I have a larger deflection zone with the softer track than I do with the stiffer track. The rail section effect is relatively small on the deflection side. Why? Because it only shows up in the beta term under the fourth root. So it's a fourth root of of the moment of inertia. So the rail term, and we have the moment of inertia, or the EI, the bending rigidity, is under the fourth root and the beta term. And so its effect is relatively small that you can see over here. On the moment side, again, dynamic load does exactly the same for moments as it does for deflections. The greater the dynamic load, the greater the speed, the higher the speed, the greater the dynamic load, the greater the moment. And again, the crossing point is the same. Moment versus track modulus. The higher moment with the softer track modulus again. Rail size has a very tiny effect because it only enters into the fourth root. So that's the effects. Okay, so the real world is not a wheel, though. Okay, up until now, we've modeled our track as a beam and elastic foundation. And we said we have a single wheel. The real world, I have two axles to a bogie, two bogies to a wagon. And then if I have another wagon over here, I have another couple of bogies here. So typically, depending on the kind of bogies we have, the distance between axles is usually of the order of 3 to 4 meters. Sometimes a little bit less depending on the design, but it's not at all uncommon. Well, you can have it down as 2 meters, so it can be 2 to 4 meters. I can see the difference between axles and a bogie. The distance between bogies in a wagon can be of the order of 10 to 20 meters. And the distance between bogies from adjacent wagons, so this is wagon 1 and this is wagon 2, that can be the order of 3 to 6 meters. So the closest distance is between adjacent axles, again 2 to 4 meters. The next closest is between adjacent bogies, of different wagons. And then for the greatest distance is bogies between the same trucks. So what do we know? In fact, let's go back one more first before we go into that question. If we look at a typical deflection curve, in fact, let's look at the sensitivities. So if we look at our deflection curves, we can see our deflection curves, the sensitivity can go up to 6 meters or greater. So if I have another axle within 2 or 3 meters or 4 meters of my first axle, that axle is going to have an effect. Same thing with the moment. If I have another axle within 2 to 4 meters or 2 to 5 meters of my axle, of my first axle, my first wheel, then that second axle or that second wheel is going to have an effect. So I definitely expect an effect from here. I might get an effect from here, and I probably will not get an effect from here. So the second bogie on the same wagon is probably not going to be very effective. The second wheel on the same, or the second axle on the same bogie is definitely going to have an effect. And the second bogie from an adjacent wagon may have an effect. And it depends. It depends on how sensitive we are. And that sensitivity, again, is a function of things like the track stiffness. In fact, the track stiffness is a very major effect onto how distances we're going to be. So if I have a very stiff track and it's a 2 meter effect, then more than likely the second axle of the same bogie will be important, but the adjacent axle, the next bogie of the adjacent wagon is not going to have an effect. Whereas if I have a very soft track, then the adjacent wagon will also have an effect. So let's look at that. So this is the deflection curve. Now I apologize, these curves are all in English, but we're going to go through them in metric in a few moments. So we'll just get there. You just bear with me on that. So this is very soft track. So this is about 6 or 7 kilonewton track. If I have 2 bogies that are about 2 meters apart, which roughly this distance. So here's wheel 1 and here's wheel 2. The dashed lines represent the deflection curves of the 2 bogies, and the solid line represents the combined curve. Now, how do I combine them? I combine them using a technique called linear superposition. Linear superposition means I basically add the deflections at both points. So I have 2 deflection curves, curve 1 and curve 2, corresponding to 2 wheels. At x equals 0, in this particular case, they're about the same value, about 1/4 inch or roughly, so I got what? I've got 25 millimeters to 1 inch, so 1/4 inch is about 6 millimeters. So this is about 6 millimeters. So I have 6 millimeters from one curve, 6 millimeters from another curve. I add it up. I get 12 millimeters over here, and that's my combined deflection. I add each of these points up. I add all the points one by one, and I get my combined curve. And you notice for very soft track, my maximum deflection is really in between the 2 wheels. And here's my uplift, which is pushed out over here. As my track gets stiffer, So this would be track that's about 21 kilonewtons. I still have my two deflection curves, wheel 1 and wheel 2. But you notice them, when I add them together, the maximum deflections is actually a little bit further out. And this gets more exaggerated the stiffer I get. So the shape of the combined deflection curve is actually a function of the stiffness. So this I said was about 21. This is about 40 kilonewtons. And you can see the deflections, by the way, are significantly lower. The combined deflection here is about 12 millimeters. The combined deflection here is about 3 millimeters or 2.5 millimeters. And this is sort of in between. This is about 4 or 5 millimeters. The same thing happens with my moments. If I have an adjacent bogey, now in this particular case, my dash curve represents one wheel, and the second curve represents another wheel. And notice here that because the change in direction happens closer, the combined curve is a little bit lower than the maximum because I'm subtracting out the moment. Let me show that to you, but let me show you that in a spreadsheet, because that's really important to see. And I'm going to switch back to the spreadsheet because I want you to understand what's happening here. Where is my spreadsheet? Okay, so you all remember this is a single wheel. Let's add another wheel. Okay, so this is the exact same problem we did here, except I said that we have a bogey. And we have a bogey which has an axle spacing of 2 meters. So the distance between my axles on the bogey is 2 meters, which is a fairly common type of distance, very standard. So I now have one wheel at x equals 0, and my second wheel is now at x equals 2,000. My dynamic load is exactly the same because say again, somebody have a question? My dynamic load is exactly the same because each wheel has the same wheel load, static wheel load. The wagon's still going at the same speed. The wheel diameters are the same. My modulus is the same. My rail is the same. My beta is the same. The only difference is I have a second wheel. So if I come back over here, this is wheel 1, which we already did. So x equals 0 for wheel 1. But now I've added wheel 2. And I've added it 2,000 millimeters away from wheel 1. So how do I solve that? Okay, it's my exact same equation, P beta over 2K, e to the minus. Now, instead of just being x, it's x minus 2,000 millimeters because I've shifted my track. I've shifted this wheel over 2,000, but I want to line it up still from this x point. So my x-axis still starts from my first wheel. I can't shift my x-axis. That would make it much too complicated. So my x is set at the first wheel location. So my second wheel now starts at 2,000 millimeters. So what I do is I have x minus 2,000 in my exponent, x minus equal 2,000 in my cosine term, x minus equal 2,000 in my sine term, and I use the absolute value because 0 minus 2,000 is a negative value. So very important. If you start getting ridiculous numbers in this graph, the first thing you do is make sure you haven't forgotten your absolute value, or you haven't screwed up your sign. Because if you forget your absolute value, you're going to start getting ridiculous numbers. I only give problems that are real. I only give problems that correspond to physical reality. So if something looks really off, if it's telling you that deflection is 20 millimeters, or the deflection is a meter, don't believe it. You made a mistake in your calculation. So notice what happens here with my second wheel. So this is my first wheel in red. My first wheel in red. Oh, hold on a second. What did I just do? Okay. So notice my first wheel in red is exactly the same as my wheel over here, just from x equals 0. It's the same wheel, the same value, 8.409. It changes at about 3,000, etc. And that hasn't changed. Changes at 2,000. Yeah, okay. My second wheel is at x equals 2,000. So the maximum deflection at 0 is going to be a lot less, because the maximum deflection is going to be at 2,000. And look, at 2,000, my deflection minus 8.49 is exactly the same as my deflection of the first wheel at x equals 0, because it's the same wheel, it's the same modulus, it's the same load, everything's the same. So my maximum, but my place where I cross the x-axis has changed, has moved over 2,000 millimeters. The place where I have my maximum uplift has changed. It's moved over 2,000 millimeters. But basically, the red curve and the green curve are the same curves, just shifted 2,000 millimeters. And you can see that over here. Just look at my values. Now, once I shift over 2,000 millimeters, my values are all the same. So to get my combined curve, all I do is I add wheel 1 to wheel 2. And that's wheel total over here. So there's wheel 1, minus 8.4. There's wheel 2, minus 2.2. There's the combined minus 10.6. So I've just basically added all these points. This is for a modulus of a modulus of 6.9 megapascals. Now, to make the point I made in the other graph, if I change this number to, let's say, 40 megapascals, look what happens. First of all, notice my deflection has changed significantly. Remember, the combined deflection was about 10, and now the combined deflection is about 2. And notice the shape has changed a little bit. Notice it's no longer the maximum in between the two, but the maximum is under the wheel. If I made this 20, my deflection is now 4 millimeters instead of 10 millimeters, 4.2 millimeters. But my maximum is under the wheel. If I go back to the 6.9, I have the case I gave you before, maximum under the wheel 10.6. Exactly the same thing happens with the moment. Wheel 1 is exactly the same from the previous case. Again, 555, 555. wheel 2, again, moment 2, P over 4 beta e to the minus beta x minus 2000, cosine beta x minus 2000 minus sine beta x minus 2000. Okay? So again, it's the same curve. Again, it's the same. Here's my red curve. Here's my green curve. It's the same curve. I've just shifted it over 2000 to reflect the position of the second wheel. And then my combined moment, I just add every point together. So again, the point I was making, the first wheel had a value of 555,49213. The second wheel was negative because it goes negative much closer within the 2,000 millimeters. So the second moment is minus 1135. So they actually subtract from each other. The combined value is 442. And you can see over here, the combined value is blue, is actually less than the combined value of each of the individuals. But in the reverse side, that's not the case. In the reverse side, it's actually a little bit higher. And this behavior changes with K value. So it's actually a little bit more complex behavior. Again, if I put a K of 20 in there, you can see how the moment values changed and how the combined uplift changed, the combined reverse moment changed. If I put a 40 in there, so look over here. You can see my combined curve is now lower than my higher curve. Any questions? Because this is important. You're going to see this again too.
Can you give us this spreadsheet?
No, but you have the spreadsheet. You have this almost the exact same spreadsheet, a very similar spreadsheet you're going to have in the problem, the class problem. So you basically get a spreadsheet in the class problem. I don't need to give you 2 spreadsheets. You already have one. If you put these values into the spreadsheet in the class problem, you will get these answers. But I want to encourage you to do the problem. So the values are a little different. So you don't have exactly the same answers right away. But you'll get the spreadsheet. The spreadsheet is in the class problem. And the spreadsheet has 2 tabs. There's one tab for single axle and one tab for 2 axles. And the problem and the class problem is the given both 1 axle and 2 axle case. So I know everybody wants to go out and practice it, and I suspect we'll have questions afterwards. Anybody have any questions now before I continue on? Okay. So this is what we just did, and now you can understand a little bit better what I mean by the deflections. Well, this is moments. Here's the deflections. The deflections, maximums, the combined deflection shapes change with the modulus. Again, this is about 7 megapascals. This is about 20 megapascals, and this is about 40 megapascals. And the moments, again, same thing, 7, 20, 40. And again, just like I showed you in the spreadsheet, with a roughly 2 meter spacing, then the maximum, the combined is actually lower than the individual one. So that's what happens if I have 2 axles. Again, what happens if I have a wagon with two-axle bogies? Now, I mentioned before that the influence zone over here, this is of the order of 10 to 20 meters. And so basically, for all practical purposes, these two bogies don't influence each other. The two axles on the same bogie has a real effect, but on the same wagon, they don't influence each other. But what happens if I had wagon 1 and wagon 2? Now here, the distance between this axle and this axle is of the order of about 2.5 to 3 meters. And so they do affect it. And so we get this type of a behavior. You can see the effect here, and you can see the superposition effect here, and you can see the effect here. We also, I don't have it here, but let's come back. And what happens if I had a three-axle locomotive? So I had another axle over here. This would also have an effect, and I would have to do 3. So I would have to do, in this particular, 2, 3, 4. Every once in a while, when I really decide to give me a hard time, and you won't get it here, but what happens if I have 2 locomotives next to each other with 3 axles here and 3 axles here? All 6 wheels will be important, will make an effect. And so we have to do linear position for 6. The mathematics is actually very straightforward. You just got to make sure you keep your record keeping properly.
Alan, can I ask a question?
Absolutely.
Where do you see that the combined moment is lower than the single, from a single wheel?
Let's go back to the spreadsheet because it'll be easier to see. It'll be easier to see on the spreadsheet.
But on the combined graph, we can see it?
Yes, I'll show it to you in the combined graph on the spreadsheet here in a second. Oh. Okay, so we're talking about moment, the deflection, or we're talking about moment, right? Combined moment. Okay, so let's look at x equals 0. The red, where's my legend? Okay, here we go. The red is wheel 1. The blue is the combined. You see how the blue is less than the red? The blue is about 400. What are the units there? About 40 million newtons millimeters. And the red's about 55. Can you see this?
Yeah, thanks.
Okay. And just to make sure, we go back up to the numbers. There's wheel 1. There's wheel 2, which, as you can see over here, is negative. So where wheel 1's positive, wheel 2 is negative. So when I add them together, I get the reduced numbers. So there's my 55 for wheel 1. There's my 44 for the combined. There's my minus 11 for the wheel 2. And so here you can clearly see it. Now, if I change, that doesn't always happen, because if I change in my modulus, it may not happen. So if I go up to 40, for example, it's still happening, but theoretically, if I went up high enough, if I spread that out enough, it wouldn't happen. Let's see what happens if I have a 3 in there. If I have a 3 in there, it's still happening, but it's just harder to see. Okay, does anybody have any other questions about combining, about anything having to do with the beam and elastic foundation for the deflection and moments that we talked about? Because we're gonna be using beam and elastic foundation today and next week and going forward. So I want you to make sure you understand it. And I know you all want to get back and try and practice with this spreadsheet, with the problem. But I just want to make sure you have the idea so far. Okay, so up until now, we've only been talking about what happens with the rail. So now let's talk about what happens with the sleeper. Okay? So this is my beam and elastic foundation track. And remember, the spring K represents the sleeper in the ballast. So again, W is my deflection, my sleeper spacing. You'll either see it referred to as A or S. Both are used in the literature, so you'll see both of them. Okay, so what happens is I'm representing my sleepers, which are really spaced apart by this distance A or S, and we're representing it by a continuous foundation. Now, this force, now remember, let's go back to our fourth order differential equation. We had a fourth order term, which is EI d4w dx to the fourth. We had a KW term, which was my foundation support term, and then we had a load term. So essentially, the KW term represents the distributed load. Let's go back and remember our units. The K is in newtons per millimeter, or newtons per millimeter squared. If I take K and I multiply it by X, my deflection, W, which is in millimeters, I end up with a term that's newtons per millimeter. If I multiply, so that's my distributed, that is essentially a distributed force. And if I take that KW and multiply it by the sleeper spacing, take KW and multiply it by the sleeper spacing, A.
Is K represent the
So I
stiffness
multiply it
combination of the
by millimeters again, and then I have a force Newton. That's now the force on my sleeper. So basically, by this force P is my stiffness K times my deflection. So this would be at X equals 0 by a convention, so at W of 0, times A over 2 on either side of it. So I got this distance on either side of it, so it's A. And the force on this sleeper over here, or let's take this sleeper over here, would be K W of X for whatever this distance X is, times A. So in this particular case, I know it's 1, 2, 3, 4 sleepers around. So this is actually X equals 3A. So the force on this sleeper would be K times W 3A times A. So the maximum force on any sleeper given by the wheel is always underneath the wheel at x equals 0, because that's where the maximum deflection is. And the maximum force is kW of 0A. We know W is P beta over 2K. So it's K times 2 beta over 2A, K times P beta over 2A times A. We can actually cross out the K's and have P beta over A over 2. So if I wanted to do a sample calculation on that, so let's go back to our spreadsheet. Okay. So my K, we know from the previous case, was 6.9. I have a sleeper spacing of 600 millimeters. So sleeper 1 is at 600, sleeper 2 is at 1200, sleeper 3 is at 1800, sleeper 4 is at 2400, sleeper 5 is at 3000, sleeper 6 is at 3600. So basically, if I go back to this graph, I have a sleeper here. I have a sleeper here. I have a sleeper here. I have a sleeper here, etc. If I want to get the loading, so I have my X. I can calculate my W of X exactly as we did over here. You can see sleeper. So, and of course, there's a sleeper here. Sorry, there's a sleeper under the wheel as well. So this is sleeper 0, which is under the wheel. This is sleeper 1. Minus 7.2 millimeters, etc. So this is exactly the same as we calculated over here. So the force on these sleepers is now W, the deflection, times K times A. So A is equal to 600. There it is. That's why I don't have to repeat it. I have it down here. Okay, so K, 6.9 megapascals. W, which varies with sleeper, times A. So you can see the sleeper, so remember, the total dynamic load that's applied on a single wheel was 160 kilonewtons. The wheel, the sleeper directly under the wheel, the sleeper that's right over here, gets 335 kilonewtons, or 22% of the load. The sleeper on either side, so the sleeper at 600 here and minus 600 here, gets 30 kilonewtons, or 19%. The sleeper at 1200 on either side of it gets about 30%, about 20 kilonewtons. Sleeper number 3 is still getting some load. Sleeper number 4 is still getting a little bit of load, maybe 5 kilonewtons. And sleeper number 5 is already down to about 1%. So you can see that for all practical purposes, the wheel load here is distributed over 1 plus 2 plus 2 plus 2 plus 2, 2, 4, 6, 8, 9 sleepers carry a single wheel load to some degree or another. Now, the percentage of load carried by a sleeper will vary significantly by the track modulus. So if the track modulus became 40, oops, a mistake in this particular one. So let's go over here. Oh, I do is I changed them. Let me see which ones I'm using. Huh. Why did that blow up? Oh, because I'm dividing by, I haven't changed B7. Something
There
just.
isn't enough space. That's it.
No, I was looking at the percentages. I was looking at the percentages. The percentages were off. Okay, we'll come back to that in a minute. So there's something happened in that spreadsheet, and I'm not sure why.
What is the difference between tie and sleepers?
Nothing. It's the same thing.
Okay.
It's another word. It's another word for sleeper. It's another word. Tie is another word for sleeper. Okay. So anyway, let's do it. Let's just stick to what I have over here. We'll change. I'll fix the spreadsheet when I find the problem. If I increase my modulus from say 6.9 to 27.6 over here, you can see that the load underneath the sleeper is increased, and the load under the middle sleeper has increased. And in fact, the distribution is changes. And this is something that we see as we increase we increase the stiffness of the track. The middle sleeper, the sleeper directly under the wheel, carries more of the load for each individual for stiffer track. So softer track spreads out the load more. You can see over here for the stiffer track, for example, that it only really goes up to about tie number 4. Here it goes out a little bit further. So using this KWA approximation, we can calculate the percent. We can calculate the load on each sleeper. We can calculate the load on each sleeper underneath the track. If I come back over here, I can do the same thing. You can do. Exactly what I just did before. Hopefully the same number too. Yes. Good. We said did that right. Okay. Everyone clear on that, or am I losing? Have I started to lose people here?
Allan, can you please explain what is the percentage for?
The percentage. Let me just share this. I'll go back to the spreadsheet. No, to the PowerPoint. Here we go. The percentage just tells me how much of each wheel load. Okay, so what happens is this. I have a wheel and I have a group of sleepers underneath the wheel. The point I'm trying to make here is the amount, this wheel's dynamic load is not carried only by this sleeper. It's also carried by this sleeper and this sleeper, and this sleeper, up to about 4 on either side. And so for very soft track, which is K equals 6.9 megapascals, this sleeper carries about 22% of the wheel load. This load, total load. For very stiff track, it carries between 30 and 40% of the load. And not as many sleepers carry the load. So I'm just trying to make the point that the load, the track, one of the purposes of the track behavior is to distribute the load through the track structure. And so it takes that wheel load and spreads it over multiple ties, not just on one tie. If you just put the sleeper on the one tie and you had no other sleepers to carry the load, then you would basically run the risk of crushing the tie underneath the wheel, because the loads will be 3 to 4 times as great. So that's why I like to think in terms of percentage. Here you can calculate the load itself in newtons, and you can see what percentage of the load's carried. Any other questions? So this is looking at it a different way. This is okay, I should actually put this slide up because that actually explains the percentage a little bit better. So here you can see the concept very clearly. This is for stiff track. So this would track that would probably be something like 40 to 50 megapascals. You can see the sleeper directly under the wheel carries about 40% of the load. These two sleepers carry another 20% each, and these two sleepers carry about another 10% each. So combined, they add up to approximately 100%.
The P is static or dynamic?
Dynamic,
Dynamic.
unless the vehicle is standing still, in which case it's static. If you park the vehicle there, it's static. But if it's moving, it's always dynamic.
What about the parallel wheel load?
That's on the other side of the. Good question. So what you're having is in the real world. I have 2 rails, and I have one wheel load here and another wheel load here. So when we talk about sleeper loading, which we'll talk about either today or next week, depending on how far I get, we're going to see that you have the sleeper sees the load from both wheels, from the full axle. But we do this analysis independently because each rail is subject only to a wheel load. So if I want to calculate the stresses in my rail, I have to use the wheel load, right? Because the second wheel doesn't affect this rail. So, or let's put it this way. This wheel over here does not affect this rail, but affects the sleeper, it affects the ballast, it affects the sub-ballast, etc. Again, you can see for a moderate foundation, takes about 24%. And so you're going to see, loads going further out. Any other questions?
What is the load for moderate in megapascal?
What's the value? Moderate would be probably around between maybe 15 to 20 megapascals.
Thank you.
And soft, I said, is about 3 to 10. Now, the beam of elastic model, like all models, has some shortcomings. One of the first ones is the liftoff. Okay, so when we do, again, when we have a deflection curve, there's an uplift. You actually don't get much uplift off of the concrete sleepers because the concrete sleepers are heavy enough to keep it down. On wood sleepers, you always get an uplift because the lift up force of the beam and elastic foundation is is heavier than the weight of the wood sleeper, but not as strong as a concrete sleeper. So that's a shortcoming, but it's an approximation, and the approximations are still pretty valid. Going into a little bit more detail, beam and elastic foundation only assumes vertical deflection. In reality, as you can see here, there is some rotation of the sleeper. Beam and elastic foundation model assumes that it goes straight down, it doesn't rotate. So there's a small error introduced by that. There's no resistance to the tie rotation. That's a small error. It assumes the springs are linear springs with no shear interaction between them. And of course, ballast does allow shear interaction. So in reality, there is a shear interaction effect. And so there are alternate foundation models. There's something called the Pasternak foundation. There's something called the Kerr foundation, etc. But again, like some of the other things I've showed you, the increase in accuracy of these models is very small, and the amount of increased work, like if you were to solve a Pasternak foundation, that's much, much more sophisticated and much more difficult than the beam and elastic foundation. As a matter of fact, after you work with the beam and elastic foundation model a little bit, after you work on it at home, you'll see it's actually a very simple model to use. It's not very difficult to use. It's a little bit intimidating when you look at it first, but it's not a particularly difficult model to use. Whereas the Pasternak model or the Kerr model or some of the other models are much more difficult to use. And their increase in accuracy is usually not worth the extra effort involved. I mean, if you're going to try to program everything, then you're going to skip everything over and go to a finite element model. So I've got a 1:45 now. Let's take our second break. Resume at 12 and see how far we go before I run out of time.
What time?
Sorry, you didn't hear me. I was muted. 15 minutes, 7 o'clock. 7 o'clock your time. We'll resume.